So we'll be relying on this theorem, the envelope theorem, to derive a number of interesting results, both in the theory of the firm but also in consumer theory. So I thought I would first derive this theorem for you. So first, considering an unconstrained optimization problem. We have a function that we're trying to maximize. We're trying to maximize f. F is a function of x and an underlying parameter phi. This function f, by the way, we'll call it the indirect objective function. So how would we go about this? We would first look at the first order condition, partial derivative of x with respect to x, set that equal to 0. We would solve and we would find a value x star, right? So solve, and x star is a function of phi, the underlying, the parameter. Now if we take the solution x star to the maximization problem and we substitute this value into the objective function, we get what's called a value function, v. And v is only a function of phi, right? So the value function is the underlying objective function which has been maximized. So we plug x star, which is a function of phi. Now you'll note here that phi appears twice. Here there's going to be both direct phi directly affects f because f is defined over phi, but phi is also important because x star is also a function of phi. Now the question that we're looking to address here is how does the value function change when the parameter changes? So what is dv d phi? And the theorem is going to tell us, I'm going to prove this for you, that this is none other than the partial derivative of f with respect to phi. So how do I go about to proving something like this? So let me first write again that the value function is a function of phi, and that's simply equal to f with x star defined over x star, which itself is a function of phi, and f is also a function of phi. And now I'm interested to look at dv d phi. So I'm going to write first the chain rule here, focusing on the indirect impact of phi on the objective function. So I can write that I have partial derivative of f with respect to x. It's going to be evaluated at x star, right? Times partial derivative of x star with respect to phi. That's the indirect impact of a change in phi on the objective function, plus the direct impact, which is simply df d phi. Okay. Let me write here just to make it crystal clear that I have f, I have x star, and I have phi, and I'm saying a change in phi changes the value of x star, which in turn changes the value of f. That's the chain rule, the indirect effect, and then a change in phi directly impacts f. Now the really important thing to see here is that because f is maximized at x star, this item here, the partial derivative of f with respect to x star, that's equal to 0. And that's just because of the first order condition of maximization. So partial of f with respect to x star is equal to 0. Right, so if you look at here, x and f, all right, we have some value, whatever, and there's a maximum point here, which is x star, which maximizes f, and at that point, right, the derivative here is equal to 0. Okay, so we can see this quite easily. So this entire term drops out, and we are left with simply the partial derivative of the objective function with respect to phi. So a change in the optimal value of a function with respect to a parameter of that function can be found by simply differentiating the objective function with respect to that parameter while holding x at its optimal value. And the idea here is that the infinitesimal change in the parameter has no impact on that optimal value and can simply be disregarded. So we're looking at the envelope theorem in a more general version in the context of constraint optimization, where we have to maximize a function f of x with parameter phi such that the constraint g function of x and phi must be equal to 0. Let's look at an interior solution from that for now. So we can write the Lagrangian, which is f of x phi plus lambda g of x phi. So the first order condition, we write that the partial derivative of the Lagrangian with respect to x, which is partial derivative of f with respect to x plus lambda partial derivative of g with respect to x, and that must be equal to 0. Partial derivative of the Lagrangian with respect to lambda is simply g, function of x and phi, and that must also be equal to 0. And we solve for this, and we're going to get two solutions, x star and lambda star. X star is a function of phi, lambda star is a function of phi. If we substitute the solutions into the objective function, we get v, which is a function of phi, which is equal to f evaluated at x star and if I now look at the derivative of v with respect to phi, applying again the chain rule, partial derivative of f with respect to x times partial derivative of x star with respect to alpha plus partial derivative of f with respect to alpha. I'm sorry, phi. This equation does not simplify as easily as before, right? Because partial derivative of f with respect to x star is no longer equal to 0. From the first order condition before, I can see that f of x is equal to minus lambda gx. Okay, partial derivative of g with respect to x times the Lagrangian, and this is from the first order condition by writing the partial derivative of the Lagrangian with respect to x. So this does not simplify so easily. This is not equal to 0 as it was before in the unconstrained scenario. I'm still going to be able to land on my feet. I substitute the solution into the constraint. So I'm going to write g plugging in x star, which is a function of phi, and that's equal to 0. This is my constraint, so I can now differentiate with respect to phi. I get partial derivative of g with respect to x times partial derivative of x star with respect to phi. This is chain rule again, plus partial derivative of g with respect to phi equal to 0. And we can multiply by lambda, both sides by lambda, so you would get this. Okay. Now I'm going to call this first equation up here equation number 1, and the second equation here equation number 2. Now I'm going to add 1 and 2. So I get, we have derivative of the value function with respect to phi is equal to partial derivative of x of f with respect to x plus partial derivative of x star with respect to phi. Sorry, this is not a plus, this is in multiplication, this is the chain rule, plus partial derivative of f with respect to phi, plus, and now we're adding from our second equation, lambda g x plus, times partial derivative of x star with respect to phi, plus lambda times partial derivative of g with respect to phi. And all of this is equal to 0. And now we can see that this entire expression simplifies. I'm going to factorize here this term, partial derivative of x star with respect to phi. So I get f of x plus lambda g x. All of these are partial derivatives with respect to x times partial derivative of x with respect to phi plus partial derivative of f with respect to phi plus lambda partial derivative of g with respect to phi, and all of that is equal to 0. Now from the first order condition, this is the partial derivative of the Lagrangian with respect to x, and this is equal to 0. This is the first order condition, so we are left with the remainder of this expression here, which is partial derivative of f with respect to phi plus lambda times partial derivative of g with respect to phi, and this is actually the partial derivative of the Lagrangian with respect to phi. So whereas before we were just looking at the objective function, and we were saying that the derivative of the value function with respect to phi was equal to the partial derivative of the objective function with respect to phi, holding x star constant. Now we can do the same thing, except we are replacing this with the partial derivative of the Lagrangian with respect to phi. Instead of looking at the objective function, we look at the Lagrangian, because this is a constrained optimization problem. Now you can find this theorem, all of this written with slightly different notation and in a different with more of a generality to it, with multiple constraints, etc. But basically this is the idea here.